to Math Concepts. The last topic that we are going to talk about in Chapter 2 on set theory is the idea of infinite sets. Now, we're going to find that infinite sets have some rather unusual properties that finite sets do not possess. In particular, an infinite set can be put into a one-to-one matching with one of its proper subsets. You can't do that with a finite set, but you can do it with an infinite set. And two, there are, in fact, different sizes of infinite sets. So it's not enough to just say a set is infinite. There are kind of different categories or classes of infinite. And we'll talk about those ideas in the next couple videos. So let's switch over to the document camera and look at some examples of infinite sets. So the key ideas, or the things that you will need to be able to do by the time we finish this section, are you should be able to construct a matching between two equivalent sets. Okay, we'll talk about some examples of that in this video. This is something you should already be able to do, but you should be able to determine the cardinality of finite sets. We'll also talk about the cardinality of infinite sets, and a related idea is be able to distinguish between the different sizes of infinite sets. Okay, so here's the basic premise. Okay, if two sets have the same cardinality, we can establish a one-to-one correspondence or matching between the elements of the two sets. And this goes the other way too. If we can establish a matching between the elements, then the sets must have the same cardinality. It's very easy to understand with finite sets. These two sets are equivalent. You remember that concept from a previous video. These two sets are not equal because they have different elements. This has letters, this has numbers, but they are equivalent because they both have 5 elements. And a simple matching between the elements might go something like this. We'll take the element number 1 and match it up with A. We'll take 2 and match it up with B. 3 matched with C. 4 matched with D. 5 matched with E. Okay, so that is a matching or one-to-one correspondence between these two sets. So they have the same cardinality. And of course, since we already knew they had the same cardinality, we knew such a matching existed. So let's take a second and look at an example that might not be as obvious. So we're going to deal with an infinite set in this example. So this problem is asking us to establish a matching between the set of natural numbers 1, 2, 3, 4, 5, and so on forever, between the set of natural numbers and this set, which we are calling D. It has the odd numbers in it. 1, 3, 5, 7, keeps on going. The generic odd number is of this form, 2n minus 1. If we just do a little scratch work here to see why that formula works, if I want to get the first odd number, I can plug 1 into that formula. 2 times 1 is 2, minus 1 is 1, gives me the first odd number. Second odd number, I plug 2 into that formula. 2 times 2 is 4, minus 1 is 3, which is the second odd number. You plug 2 into this formula, you get the second odd number. You plug 3 in, 2 times 3 is 6, minus 1 is 5, and 5 is indeed the third odd number. Okay, so this expression gives us a general odd number. Okay, now the matching between the two sets isn't that difficult. We would take 1 and match it up with 1. We would take 2 from N and match it up with 3 from D. 3 gets matched up with 5, 4 with 7, and so on down the line. So in general, the matching would go like this. Match up little n from the natural numbers with 2n minus 1 from the set D of odd numbers. Okay, when you have infinite sets, you have to tell me what to do with a generic one. If you establish the pattern just with the numbers, I don't know what's going to happen after that. Okay, if you just establish it here, I would have to assume that pattern continues. This is making it explicit. Any natural number n is going to get matched up with this odd number. Okay, so if I wanted to know what 11 got matched up with, well, if n equals 11, I plug 11 in here. 2 times 11 is 22, minus 1 is 21. So 11 would get matched up with 21. Okay, so we've got to give the matching like this. Now, you might notice that the way the question was written, it almost contains the answer, right? You just take this and match it up with that. Okay, and this is a one-to-one correspondence. Every element of the set of natural numbers gets matched up with exactly one odd number. And if you give me any natural number, I can tell you the odd number that it gets matched with using this formula. Okay, you want to know what 25 gets matched with from the natural numbers? 25 would get matched with 2 times 25 is 50, minus 1 is 49. So 25 from the set of natural numbers gets matched up with 49 from the odd numbers. Okay, now you might notice that this set of odd numbers is in fact a subset of the natural numbers. Now, what we just showed by producing this one-to-one correspondence was that the set of natural numbers was equivalent to the set of odd numbers. So they both have the same cardinality. Any set that is equivalent to the natural numbers is called countably infinite, and this cardinality is denoted by this symbol right here. This cardinality is denoted by Aleph naught. Okay, that's my best attempt at writing this symbol. It's actually the first letter of the Greek alphabet. Okay, so any set that you can put in a one-to-one correspondence with the set of natural numbers is called countably infinite, and that is the symbol for its cardinality. In our next video, we will discuss sets that have different cardinalities, infinite sets that have cardinalities that are different than Aleph naught.